here as well. Okay, so hopefully we have high definition video from my camera and high quality voice from computer. I'm going to combine them, see what I can get. Okay, so here is the stuff that I'm going to discuss today. I'm going to recap quickly the del operator, okay, that we talked about last week. I'm going to talk about the gradient and divergence. Again, we are recapping the Tuesday lecture. We move on to curl. We're going to look at the product rules. Okay, so it's going to be technically expansion of the product rules that you know for simple derivative. Okay, we're going to look at them here. And then we're going to look at the second derivatives, which are interesting. And there's a lot of application of second derivative of the del product, meaning that applying the del operator, meaning that applying del operator twice on a function. Okay. And as I said, that happens very often in physics. Okay, some of the second derivatives. Okay, any question from the last lecture?
Nope.
No, everybody is good, happy. Okay, so far it's clear what we are discussing in class, more or less. Okay, that's good. Are you guys reading the textbook? You should. Okay, so get started on that. Otherwise it's going to be, it just piles up. Okay, you're going to find yourself having a lot of reading to do. Okay, if you read as I teach, it's going to be a lot easier. Okay, a lot easier. And by the way, all my teaching is from the textbook. So if you do it quick, it's going to be very familiar to you, and you're going to get that very, very rapidly. Okay, so the del operator. Okay, so we talked about the gradient first, and we defined del operator as the unit vector in each direction times the partial derivative in the same direction. So it's going to be like x hat times partial derivative with respect to x plus y hat times partial derivative with respect to y and z hat d over dz. Okay, so this is an operator, and this is technically a vector operator. A vector operator can be applied on scalar fields as well as vector fields. Okay, so our starting point was applying the vector operator del on a scalar field. Okay. So t is technically a function of x, y, z. This is a scalar. You apply the vector operator del on these, and the result is going to be a vector. Okay, and our example for the scalar operator was like temperature in my office. Okay, temperature is a scalar, but it can be dependent on 3 variables. Okay. You have a thermometer in my hand. Okay, I get a thermometer in my hand. If I move my hand, I will have different readings. Okay, and that different readings depends on x, y, z. If you apply the operator on that function, it's going to tell you how fast and in what direction and how the temperature is going to change. Okay, so at any point, if you apply the operator, you're going to get a vector. What is the concept? What is the meaning of that vector? I want you to answer. You can unmute.
Oh, isn't it the highest change?
It's so vector has direction and also magnitude, right? So the gradient of t here, okay, so technically refers, first of all, it shows the direction of the greatest change. Okay, what direction you should move to see the greatest change. And also the magnitude of that is going to tell you how fast and what the rate of change you're going to observe. Okay, so that is the concept of gradients. If you do it in 2 dimensions, the same meaning. If you do it 1 dimension, that's exactly the slope of a line. Okay, if you do it in 1 dimension, that's simple derivative. Okay, so remember that. Gradient in 3 dimensions, the direction of the greatest change. In 2 dimensions, the same meaning. In 1 dimension, that simplifies to simple derivative, okay, which is a slope. And that is technically the magnitude of the rate of change. If you move on the x-axis, what you're going to observe on the y-axis. Make sense? Okay, so this is the gradient. And then del operator is a vector operator. You can also apply it on vectors, okay? One way to do that is doing the dot product. Imagine we have the vector field defined as Vx times x hat plus Vy times y hat plus Vz times z hat. Okay, so this is a definition of a vector field. And if we apply the operator using the dot product, okay, the combination is divergence, and the outcome of that is a scalar. And that is equal to dvx dx plus dvy dy plus dvz dz. Looks good? And this is divergence. What is the conceptual meaning of divergence? Kind of obvious from the name, right? The meaning is you have a field, it's a vector field, so you can imagine that in terms of the arrows going all the way in one direction or other directions, or converge or diverge, okay? So divergence means something like this. You have vectors originating from one point and going away. Okay, this is the most simple case of a vector field that clearly shows a sort of divergence. Okay, if you want to think about that more mathematically, is this. You can imagine one small infinitesimal cube, okay, and look at the vector field on each part of this, okay. So on the top, let's say you have a vector like this, on this side you have like this, on this side you have something going in. The divergence is going to tell you if you add up all the flux from all 6 different sides, okay, so from each side you have some flux either coming in or going out. If you add up all the flux, it's going to be either positive or negative. Okay, if it's positive, you have divergence. If it's negative, you have convergence. If it's 0, okay, if it's 0, you don't have any divergence. Okay, in physics, we have certain fields that actually known to have 0 divergence. Okay, magnetic field is one of them. Flow of the fluid, which is uncompressible fluid, is always non-divergent. Okay, that means if you look at the water flowing in the river, if you imagine one single small cube inside the river, okay, and look at how much water is coming in inside that cube, hypothetical cube, how much water is coming in, how much water is going out. Because water is not compressible in a river, what happens is that the amount going out is always exactly the same as the amount coming in. Okay, so the vector field that defines the speed of water in a river is a vector field, okay, and that does not have any divergence. That's another example. Make sense? Okay, so we did a couple of examples on divergence, I remember, right? We had we talked about a couple of different fields. One of them was the field being like x times x hat plus y times y hat plus z times z hat. Okay, so if you have a field like this, if you want to picture this, it's going to be like something like that. So if you have x, y, z, let's just look at the x, y, and z is going to be very similar to this. If you look at the x, y plane, you're going to get vectors like this. Not right here, but like this.
Professor,
Yes.
What have you written in front of the vector v on the last line?
This vector,
Yeah,
I'm going to say number 1. I'm going to have a couple of examples.
Thank you.
Okay. As soon as it's not legible, please let me know, because from my eyes, it's very legible and big, okay? I don't know what you're seeing on your computer, so tell me. And then you're gonna get field lines like this. Okay, and if you go away from the origin, you're gonna get stronger arrows, stronger field lines, okay? So divergence of this, if we calculate, is a positive number 3. Okay, being positive means they are divergent. Okay, if we had negative instead of positive, okay, so let's say switch to negative x and negative y, negative z. What happens is that the direction of these fields are going to change. Okay, we get something like this: x, y. We get field lines towards center. Okay, and if you look at this, the divergence becomes -3. Okay, so let me write here. Okay, so this is one example that it's very obvious diverging and converging. Another example which is not that obvious is if we have a field and it's in one direction, okay, all the fields going in one direction, but the value change, okay. So let's look at that, and that's going to be the last example on divergence. Let me get rid of this.
Professor, I couldn't see the very last line. I was trying to change my screen to make it so I could.
Okay, but I wrote that right here again. I know
Okay.
this is going out of one. So the last line was this: divergence of V with the negative signs is going to be -3.
Okay. Thank you.
Okay. So let's now look at another field. And that is example number 2. V is Z times Z hat. Okay, so if you want to draw a field like this, I'm going to do it on the top here. You have functions of if this is Z direction and if this is X, you're going to get lines like this. Pretty uniform in one direction, okay? But then if you move up on the Z-axis, you're going to get bigger numbers, okay? So you get something like this. And then if you move higher, you're going to get stronger field lines. Okay, so if you look at this, you're going to see parallel lines. The stress is increasing, okay? It doesn't really look like diverging like previous example, but if you look at the divergence of this, divergence of V, the first derivative 0, the second one is 0, and the last one is 1. So the divergence is 1, okay? It's positive. And the way you should look at this is, again, if you consider one cube here, okay? And then if you want to look at what flux of the field going in, what flux going out, what happens is that from the sides, you don't have any flux coming in. From the bottom, you have some flux coming in, and from the top, you see more flux going out, okay? So within this small cube, you have more flux going away rather than coming in. Okay, so in that sense, this is a diverging field, even though all the lines look parallel to each other. Make sense? Yes?
Oh, sorry, can you say that again? I didn't get that one.
Okay, so the field lines look parallel, okay, but if you imagine one cube, the red cube I draw here, okay, I don't know if it's visible for you or not. Okay, if you look at one cube, and if you calculate the flux going inside the cube and the flux going outside, from the sides, you don't have any flux coming in, okay, because all the field lines are parallel to the surface. From the bottom, you have some flux going in. From the top, you have more flux going out because it's at a higher level, okay, and you have a stronger field at the higher level. Combined, if you add up all the flux, you're gonna have a negative value coming in and going out. You have more going out than coming in, okay? So that itself becomes a definition of a diverging field. Within that box, you have more flux going out.
Okay, thank you.
You're welcome. Sounds good? Any question on this or on divergence as a whole? If not, I'm gonna move on to curves. So we completed the recap of the Tuesday, and I'm gonna look at the curve, which is a different form of applying the del operator on a vector field, okay? So let me get rid of this and gradient. Okay, so del operator, and now imagine again we have the vector field V, which is Vx, x hat, Vy, y hat, and Vz, z hat. Okay, and then curl is using the cross product to apply del on a vector. Okay, and the cross product, if you remember, using the component form, we had x hat, y hat, and z hat, the first line. The second line should be the component of the first vector, which is an operator here, meaning that you get d over dx, d dy, and d dz for the second line. The last line are the components of our vector that become vx, vy, vz. Okay, so this is the curl. And obviously it's a vector. Okay, so if we want to expand this determinant, okay, what we get is in the x hat direction, we get derivative of vz with respect to y minus derivative of vy with respect to z. Okay, so we get dvz over dy minus dvy over dz. The second term for y hat has a negative, so I'm going to write positive y hat and then apply the way I'm calculating the determinant of the 2 by 2 matrix, and that's going to be dvx over dz minus dvz over dx. Okay, and then another component in z direction is going to be z hat times dvy over dv over dx. Okay, dvy over dx minus dvx over dy. Okay, looks good. So we have vector in 3 dimensions. Each of them have all these derivative components, and interestingly, each derivative, if you look at them separately, you have derivative of the component of the vector in one direction with respect to another direction. Okay, so this is dvz over dy, dvy over dz, and all like this. You don't have any terms similar to divergence that you're taking the derivative of the component with respect to the same direction. Okay, and this is all about curl. Okay, derivative are one component through the other one. And what is the meaning of curl? Okay, this is very mathematical definition. Looks long, doesn't look really beautiful. Okay, but the conceptual framework of the curl is very nice and beautiful. Curl calculates how the vector field swirls around the point, okay? So technically, if you have a vector field going like this, around like this, the curl of this is going to be a positive number. Okay, so this, a vector like this has a curl, has a non-zero curl. Okay, and curl is a vector, so it has a dimension as well. Okay, sorry, it has a direction as well. Direction of the curl is actually related to the direction that the vector field is swirling, and you can find that direction using your right-hand rule. Okay, so if you look at this, I showed a vector field that is curling around this way, swirling around this way. If I use my right-hand rule and put my fingers in the direction of the, not now, sorry. And if I put my fingers in the direction of the curl, right, my thumb is gonna show the direction of the curl vector, okay? So in this case, if, let's say this is X direction and this is Y direction, the curl of this field is gonna be in Z direction, okay? And I'm gonna show you one example for this as well. Okay, so far makes sense? The mathematics here makes sense? It's not beautiful, but it's very useful. Okay, so let's do one example for curl, which produces a vector almost like this. Okay, so let's get rid of this. So we have vector field V being negative y times x hat plus x times y hat. Okay, so negative y times x hat, x times y hat. Okay, let's first try to draw this and see what vector field it represents.
Professor?
Yes.
Real quick, I think for your curl, is the second term for the y hat before that, is that supposed to be negative or plus or minus?
It has to be negative, but I put positive here and I switch the terms inside.
Oh, okay, I see.
Let's check if I did that correctly. So if I put negative, I should do dvz over dx minus dvx over dz. Okay, so what I did here, I just switched the two terms.
Okay, I see. Thank you very much.
Okay, yeah. Good question. Okay, so this is x and this is y. I'm gonna try to draw this, okay, and see what we get. Imagine we are on the x-axis, so all the y values are 0. So this term completely becomes 0, okay? If we are on the x-axis, the only terms we get is x times y hat, okay? So that means, right at the origin, we don't get anything, right? But if you move on to the positive x-axis, the x value is increasing, okay? And that's gonna give us a vector actually in y direction, not x direction, okay? And that makes it interesting because we get field lines like this, and this, and this. The more we move away from the origin, we get a stronger field, okay? And if we move on the x-axis, move further away, we get a stronger fields in the y direction, okay? If we move on the negative side, we get very similar thing, but the x values are negative. So it's gonna be kind of non-symmetric to that, and we get fields lying like this, okay? The more negative, the stronger negative value in the negative y direction, okay? So these are the kind of field lines we get if we move on the x-axis. What if we move on the y-axis? If we move on the y-axis, all the x values are 0, and we get negative y times x hat. If we move to the positive y-axis, at the origin we get nothing, but a bit above that we get positive value of y times x hat, but here we have a negative sign, so it gives us a vector in this direction. Okay. The higher y value, the stronger field we get. Something like this, right? And if we go to the negative sign, likewise, we get something similar in the other direction. Looks good? So this simple equation is giving us a vector field that obviously is swirling around the z-axis. Okay? Makes sense? So this simple equation, this figure represents this simple equation. Okay? Now let's look at the curl of this V. Okay? So the curl of this we're going to look at all these values, okay? So the first term is x hat times dvz over dy. Is there any z component? No. Okay, so dvz is just 0. And then we have dvy over dz, okay? Is there any z dependent on the y component? No. So the x component, both of these derivatives are 0. Okay. And time plus y hat times these two derivatives. dvx over dz. X component does not have any z dependence, so that becomes 0. dvz over dx. vz is 0, so we don't get anything. So this is again multiplied by 0. Okay. The last term in the z direction is dvy over dx. So vy is this term. Okay. dvy over dx is dx over dx here. So we get dx over dx from the first term. The second term is negative dvx over dvy. What is vx? Negative y. So we get d negative y over dy. Okay. So what is this? This is 1. The second term is negative 1. So 1 minus negative 1 is in the bracket times z hat. Okay. So the curl is equal to 2 times z hat. Is a positive number in the z direction. Okay. So the curl of this field is in z direction. If you look at this, we have this field line swirling this direction. Okay, if I use my right hand and my fingers around the field lines, my thumb is showing in the z direction, going away from the board. Okay, so the curl is in z direction and shows a swirl of the field lines around the z axis. Make sense? Isn't it beautiful? Hopefully it is. Okay, thank you, Josh. Cool. Any question on this? No? Okay. So
On for the z, what does it say after the second term in the parentheses?
the second term where? Here?
Yeah.
This is negative y.
Oh, gotcha.
And negative y comes from this.
Okay, thank you.
Looks good. Okay, so we covered this one as well. And the next thing are product rules, which are interesting. Supposed to be very simple, but if we discuss that, that's a bit of challenge as well. So shall I erase all this board here? Okay, everybody's happy? Let's do that. Okay. So what I'm going to do here, I'm going to start with basic rules when you combine two different functions and then take derivative. Okay. So if you have one-dimensional function, that's going to be very easy and obvious to you. But I'm going to expand that and kind of explain what happens if you apply now gradient, divergence, or curl. Okay, some of them are very easy, make sense. Some of them are a little bit challenging. Okay, so it's a very good practice going through them one by one so that we have now a clear idea. If we encounter any curl applying on a combination of function and not only one function. Okay, so for simple derivative, if we take the derivative of, let's say, d over dx, adding two functions together, okay, you know that becomes like df dx plus dg dx, okay. The same rule applies to all gradient, divergence, and curl. So that means if you have gradient of one function plus another function, you can write that expand that in terms of gradient of the first one plus gradient of the second one. For the divergence, the same thing. So you have divergence of two vectors. Okay, I'm going to use A plus B. This is equal to divergence of A plus divergence of B. Okay, so how can you prove each of these ones? You can just expand, write divergence in terms of three partial derivative, and then you can go from here to here. Okay, the practice of that is easy, a little time consuming, so I'm not going to go through these steps. I'm just going to show you. Okay, and now you can imagine the same thing is going to happen to curl. If you have the curl of A plus B, okay, and that is equal to the curl of A plus curl of B. Okay, so this is for addition of two functions. Another thing, if you take the derivative of a constant times a function, okay, imagine k is a function, sorry, k is a constant and fx is a function. That is equal to k. You can take the constant out and then take the derivative of df over dx. Okay, the same thing happen for all gradient, curl, and gradient, divergence, and curl. So if you are taking the gradient of a function and multiply constant by that function, okay, this is equal to k times gradient of f. Okay, this is for gradient. The same thing goes for divergence and also curl. Okay, if you have divergence of ka, you get k times divergence of a. And if you get curl of a constant times a vector, you get that constant times the curl of the vector. Okay, I can put them in parentheses as well, something like this. Okay. And what about if you have the product? Okay. If you have the product d over dx times fg, right? You have two functions, both function of x. You take the derivative. You know that the product rule says that it's equal to f times dg over dx plus g times df over dx. Okay, so here f is not a constant, g is not a constant, both of them are functions, and they are functions of x. If you take that derivative, you will have two terms like this. Okay. Now, if you want to think about this product and you think about how the curl and gradient can really work on this, there are multiple ways that you can combine two functions, either a scalar function or vector function, to get a product and then apply the curl and gradient. Okay. The point is that this product could be, let's say, if it's a scalar, it could be product of two vector fields, or it could be the product of two scalar fields, okay? So I cannot easily expand this one the way I expanded these ones. It has multiple ways that we can make the product, okay? So I'm gonna go through this, and I'm gonna explain in what forms we can have the products in terms of the combination of vector and scalar fields, and then how we can apply the gradient, divergence, and curl on this one, okay? So the first two examples, kind of trivial. This one, not that it's not trivial, but there are multiple options you can make a product, okay? So that's what I'm gonna do next. Okay, so let me erase these ones because I need the whole board. Okay, so I'm going to show different ways. Imagine F and G are a scalar field. A and B are vector fields. Okay. Now the way we can combine these ones, multiply them by each other. One way is F times G. Okay. So we have two scalars. And obviously this is a scalar. I'm gonna write S in parentheses showing that this is a scalar. Okay. So two scalars give us a scalar. We can do A dot B, okay? Two vectors dot product, okay? So two vectors, and I do the dot product here, and that's gonna give me a scalar as well, okay? Another way, F times A is one scalar times vector. So here I have a scalar times vector, okay? And that is giving me a vector, okay? And the other one is the cross product of vector by vector. So two vectors cross product, and that's gonna give me a vector, okay? So there are four different ways we can multiply fields, vector and non-vector. And 12 of them gives me a scalar, and 12 of them give me a vector, okay? So now if we want to apply gradient or divergence or curl on these ones, you can see if we have this combination, because we are getting a scalar, the only option we have to apply them is only gradients, okay? Gradient applies on a scalar field, but divergence and curl only apply on vector fields, okay? So from this one, the only way we can apply the del product is the gradient of F times G, okay? The second one is also a scalar, so the only option I can apply del product, del operator is the gradient of A dot B. Okay. This third one is a vector. So there are two ways I can apply del product. One of them is the divergence of F times A. The other one is the curl of F times A. Likewise, for the last one, it's a vector, so I have two options. I can do the gradient, I can do the divergence of A cross B, and I can also do the curl of A cross B. Okay, so how many ways? There are 5 different ways. I'm gonna number them 1, 2, 3, 4, 5, and 6 different ways. We can have the products, and we can apply gradient, divergence, and curl on this one. Okay, so what I'm gonna do next is I'm gonna erase this part and also the top part and expand each of them. and say how we can expand these terms to get rid of the multiplication and have either gradient or divergence or curl applied on every single function. Okay. Sounds good so far? It's clear what I'm trying to do? Yes? Okay. So let me get rid of this. If I had bigger board, I would have moved just horizontal in front of them, but I don't have that one. So I'm going to get rid of this and write everything from the top here. Okay, so number one is gradient of f times g. Both of them are scalar, okay? And that is very similar to regular one-dimensional derivative. That's going to be equal to f times gradient of g plus g times gradient of f. Is it vector or a scalar?
Scalar.
This is the combination multiplication is a scalar. We are taking a gradient of that. So the gradient is a vector. And the terms here, we have two terms. F a scalar times gradient of g, this is a vector. So the first term is a vector. The second term, g times gradient of f. The gradient of f is a vector. G times that is a vector. So as a combination, this gradient is a vector. And I should write gradient of a scalar field is a vector field. Okay, so I'm going to write v here. Make sense? And the second term we have is the gradient of the dot product A dot B. Okay, so we have gradient of a scalar field and it's going to be a vector as well. Okay, so let me double check my solution here. Give me a minute, I'm gonna check. I think my notes is not complete on this part. Just to make sure I don't say anything wrong. Okay, yes. This term is really long. Okay, there's no way you can remember this. So the gradient of the dot product becomes A cross curl of B. It has four terms plus B cross curl of A. Okay, the first two terms. And then we have plus A dot del times B plus B dot del times A. Okay. So the gradient of this is going to be four terms with cross product, the first two terms, and with dot products with del times the vectors in the second term, in the third and fourth term. Okay. Each of these terms are vector. Okay, so the combination as a whole is a vector. Okay. So number three is the gradient is a divergence of f times a. F is a scalar vector. F is a scalar field. A is a vector field. The combination in the parentheses here is a vector, and divergence of that should be a scalar. Okay. So divergence of this is f times divergence of A, okay, times plus A times gradient of f. Okay. Number 4 is the curl of the same thing. Okay. And that is equal to F times the curl of A minus A cross gradient of F. Okay. So we did 4 of them. The last one is the divergence of number 5, not the last one. Number 5 is the divergence of a curl. And divergence of the curl is, it's going to be a scalar that is B dot curl of A minus A dot curl of B. And the last one is the curl of the curl. The curl of the cross product. Okay. Let me again double check it with my notes. Yeah, that is B dot del times A minus A dot del times B plus A times divergence of B minus B times divergence of A. Okay. So you see 6 different possibilities. Okay. Some of them are relatively simple. You can remember. Let's say the top one is a gradient of the multiplication, which is very similar to the rule that we had for simple functions. Okay. So it's F times gradient of G, G times gradient of F. So this is something you can somehow remember. Okay. This one, you can somehow remember that. This one, the divergence of F times A is F times divergence of A dot gradient of B. Maybe this one you can remember this as well. Okay, so these two can be memorized. One of them, this one maybe, okay, this one maybe, but the last one, let's say look at number 6 or let's look at number 2. Is this something you can memorize? Do you think anyone memorizes this? No. Okay, so what you should do is that you should just remember there is a way to expand the gradient of a dot product, okay? And these things happen, sometimes you need to use it very often, not very often, but sometimes. So what happens is that if you look at every electromagnetic book, there is a cover page or the last page somewhere that they have summarized these ones, okay? So if you encounter any multiplication like this, you should just find the book and go to the first page or last page or somewhere. There should be a list of this, and then you can use this. Okay. In many of the applications that we have in this course, even though some of them look very complicated, this one has 4 terms, this one has 4 terms, but oftentimes some of these terms very quickly summarize to 0. Okay. Imagine if you are working, let's say, with magnetic fields, and then divergence of the magnetic field is always 0. Okay, so things like that happens as well. Okay, so don't be too scared of the complexity and the length of equation. I know they are not beautiful, but you don't really need to memorize these. And if you will encounter any of these, there should be a page, cover page. I mean, let me look at the textbook where this is. You know, this is really the cover page. So from the beginning, the cover page has a list of these ones. Okay. So this is pretty much how we deal with these equations. Okay. Understand the concept and understand where you can find the expansion of these ones. Make sense?
Yeah, and all of those are vectors, correct? ones you get?
Not all of them are vectors. Let's look at them, go through them one by one. The first two ones are the gradient of a scalar. So this is vector, this is vectors.
Yeah.
This is the divergence of a vector. So this one is actually a scalar. The second one is the curl of a vector. So this is a vector. This one is divergence of a vector. So this is a scalar. This one is a curl of a curl. This is vector. Okay. So
Awesome, thank you.
we have two scalars, 1 and 2, and the rest are vectors. The one that is giving you a scalar is divergence. Divergence always gives you a scalar. The curl and gradient gives you a vector. Make sense? Any more question? No? Okay, so what time is it? This is 10:27. Okay. So what I want to do, as usual, I always cover less than what I'm trying to cover. Okay, so I'm going to stop here, product rules, and I'm going to start second derivative next week. That is an interesting discussion. Okay, so what happens is that I want everybody now, let's go to critic. The way I schedule this at today, September 3rd, at 10:30, you should be able to see the quiz I posted. Okay, so I want everyone log into the critic and see if you can see the quiz, and that's going to be a couple of minutes. Okay, so until then, you know what? Just stand up, stretch, have a cup of water, relax a little bit, and come back at 10:30. Okay, 2 minutes break, and then we're going to look at the critic and see what we have there. Okay, I'm going to do the same. Okay. All right, so have you received the quiz? Do you see that?
Yeah.
Okay, so do you see the question?
Yes.
So there's an objective, right? And there is an instruction for that. So do you see the objective? Let's go step by step. Do you see the objective?
Yeah.
Everybody?
Yeah.
Okay, if someone cannot see that, just say something or type in the chat. I'm looking at the chat message too. Okay, so the objective here is three objectives. First of all, I want you to submit your work, okay, and that work is write something on the paper, quick explanation, okay, you are not gonna get real credit for that, but something very quick. Piece of paper, take a picture, and explain something, record that with your phone or from laptop, very short, 30 seconds, ideally 1 minute maximum, okay? And you do that, then what you can do is that the way I see on Critic, you can submit picture or PDF, which is your paper, and you can also submit a video. Okay, so you're gonna submit two files. And second part, so you have time until tonight, 10 p.m. to do your submission. Once everybody did the submission, then it's time to evaluate other people's submission. You will have the chance to look at 5 other submissions and grade them. Okay. Once you submit, you don't need to write your name on top of the paper. Ideally, you don't want to write it so that you stay anonymous. Okay. Because you submitted through the Critic, eventually I know who submitted what. Okay, so don't worry about your submission gets lost and I cannot find the name. Okay, don't leave your name, and when you are recording the video, you don't need to record your face, just record your voice. Okay, record your voice and show something on the paper. Explain, like, from this step to this step, I did this because of this, I did this because of this, and that's okay. And do it quick. Okay. Then you have 24 hours to review 5 of your classmates. Once you do that, then you have another step that you log in and you look at how your peers reviewed your work, okay? And you get the feedback on that as well. Okay, so basically 3 steps, okay? And once you do that, there's also a rubric I posted here. This is kind of generic rubric for science and mathematics questions, so I'm going to use that the same. Glance through that rubric, okay? Don't be too critical and don't try to adhere too much to the rubric, okay? Just get some idea. There are 7 steps, 7 fields, and try to take that as a guideline and then use on your own logic to grade your peers, okay? So submission by the end of tonight, 10:30, and then you have 24 hours for the review, okay?
For the real quizzes, will it be the same like 10:30 submission?
Okay, the real quiz, I'm not gonna give you 12 hours. It's gonna be much less than 12 hours. Ideally, 30 minutes to write it and record it, and I'm gonna give you 15 minutes to really put the files together, take picture and upload it. I know sometimes upload takes time, but I'm gonna give you 15 minutes for that.
Do you want us to do this one right now?
Ideally, if at least some of you can try it and give me feedback how it's working, I want to make sure it works. But if you cannot do it right now, again, you have time, but I want every single of you give me some feedback. Was it easy to do it? If there was problem, what was the problem? The reason is that I need to communicate with the company and they're gonna fix all the errors, okay? And that's, I really want to make sure we get the most out of this platform. I know they have a lot of customers, they're a class of 1,000 people are using it. So probably, I know it's very well tested, but we need to make sure that it meets our needs as well. And that's very important for me.
I have a question about uploading a video. Can we upload it directly to the site, or do we have to create a video on a different platform?
Yes. Okay. Initially, I thought you need to upload somewhere else and upload the link. but I noticed that yes, you can upload the video file directly on this. Not very long video files, okay? Again, maximum 1 minute, and that should be doable.
Okay, thank you.
Professor, I have a
Yeah,
question.
sure.
We have to give you feedback after doing the quiz, right?
Yes.
So do we email you our feedback or?
No, it's on the same platform. Actually,
Oh.
the feedback is like you are grading your peers, okay? And you really give them a grade.
Oh, okay, okay.
And each of you have some grading power, and that's very interesting for big classes and very long courses. So I know in some courses people use it every week, so the students have like 17 chance to grade their peers. And there's also a feedback on feedback. So if one student is really doing a superb job grading other students, they can be identified through data analysis of the course, and those students will get higher grading power. Okay, so for this course, now everybody has the same grading power. And I think that's gonna remain the same until the end. It's a very interesting platform, and there's been a lot of research done on this. And the main purpose of grading others at the end is your own learning progress, okay? Because it's a known fact in education. You know, I can explain things to you guys, okay? But I learned these things about 20 years ago, okay? The way I explain sometimes is not the best way, even if I try so hard. But if you look at your peers, what they do, and see what kind of mistake they do, it's an excellent learning process for you, okay? At the end, the whole purpose is not just grading each other, the whole purpose. When you grade 5 other students, that's learning step for each single of you. And I want that to really happen.
And so we record ourselves doing the problem?
Okay, what you should do is that you do the problem, okay, take your time, quiet, do the problem, write it down. After you write it down, take your phone and record the step by step, what you think, what you did, and why you did that.
Okay.
Okay.
So I have a question.
Sure.
So I just want to make sure that I understand how to properly do it.
Okay.
So is me recording the solution as I'm doing it by
Yeah.
explaining
So
step by
first do it, because see, if when you are solving the quiz, it's gonna take like 25, 30 minutes, right? So you don't want to record all the 30 minutes, and you don't really want to do that, because if you're doing it, you're gonna do mistake after mistake until you figure out how to do it, okay? So take your time, do the quiz, write it down, and once you write it, it's complete, then start recording yourself, just explaining what you did. Very quick.
Okay, thank you.
Clear? Okay. So is there anyone who, so I see in the platform that 2 students has not yet, okay. Adrian, are you here? Adrian? Let me see. Okay, I don't see Adrian here. And okay, no, he's not here and he is not registered. Okay, so there's 1 student who has not enrolled yet. Others, I see 23 enrollments. And so everybody here has seen the quiz so far. So far it's working okay, right? Okay, that's good. And yeah, okay, so let's work on it. One more question I have. Is there any student here who has class right after this class?
I have class at 11.
At 11, okay.
Yeah.
So let me think about that, because I wanted to give you 15 minutes for uploading. That means 11 to 11:15. And if you have class starting right at 11, that 15 minutes is not useful for you. And okay, so probably I'm gonna start the quiz. The real quiz I'm gonna start early during the class so that you have that 15 minutes for uploading. Yeah. Okay, let's do that. Okay, so your job, guys, is now looking at the quiz, it's very simple, okay? It's good to learn it. There's actual question, okay? It's good to learn it, but the main purpose is testing this. And please upload as soon as you can, the latest 10:30 p.m. tonight, okay? And anything happens, give me feedback. Write me an email. Okay, very good. Any question?
Yes, Professor.
Okay.
Would we be allowed to just share a screen recording with us explaining over the screen recording? Like
That
if
is
I have a
fine too.
tablet,
Yes,
basically
yes,
I'm
we
writing
can
the
totally
information.
do that. You can take a picture, okay? So what I don't want you to do is this. Don't write on a screen with bad handwriting. I don't like that, okay? Write on a piece of paper, your own handwriting on a paper. Take a picture and you can show that picture on your screen, okay? And then you can do voiceover. And with mouse, you can explain part by part. That's totally fine. And that's perfect actually, because that will have a very high quality.
Okay, thank you.
Okay. Okay. Any more question? Okay. So I let you guys work on it, and I'm looking forward to get your feedback. Okay. Thank you, everyone. Have a nice day.
Thank you,
Thank you,
Professor.
Professor.
Thank you, Professor.
Bye.
Thank you.